And we'll talk about alcohols today and a little bit tomorrow. So what do we mean in organic chemistry by alcohols? Well, it's more than just the beverage, right? Or the rubbing alcohol. Those are types of alcohol. But in terms of organic chemistry, it's a functional group. And it's like a derivative of water. Now, what we mean by that is, remember that water is HOH. Well, if you just replace one of those H's within our group, keeping in mind that that letter R is just an abbreviation for some carbon-containing group of atoms, like an alkane or alkene or aromatic group, something like that. So organic derivatives of water, one of water's hydrogens is replaced by an organic group. Okay? Specifically, the term alcohol is used when the OH group is attached to an sp3 hybridized carbon. So the term alcohol is specifically applied to an OH group connected to a saturated sp3 hybridized carbon atom. It's kind of redundant to say saturated and sp3, but because they're one and the same, but nonetheless. Now, the other term that I will talk about here is hydroxyl. And I believe I mentioned this before, but just to get it into our notes for sure, sometimes it's not referred to as an alcohol, but it's referred to as a hydroxyl group. And that would be the case whenever you've got other functional groups present that maybe take precedence over the alcohol functional group. So they might say, oh, well, the hydroxyl group is on carbon 3, because on carbon 1, there's something more important, like maybe a carboxylic acid or something else. So you may see alcohols referred to as a hydroxyl group as well. Okay, and also there's a special name for when the R is a benzene ring. It's called phenol. So phenols contain the OH group connected to a carbon in a benzene ring. And they have some unique properties and some unique reactions. So they are sometimes classified separately from other alcohols. Okay, so we have learned about primary, secondary, and tertiary. Now we're going to adapt that to our discussion about alcohols, because they are classified along those lines. So classifications of alcohols are based on the number of organic groups bonded to the hydroxyl-bearing carbon. So whatever carbon has the OH group on it, how many other carbons is it attached to? If it's attached to one other carbon, we call that a primary alcohol. If it's attached to 2 other carbons, we call that a secondary alcohol. And if it's attached to 3 other carbons, we call that a tertiary alcohol. Now, we've encountered these up to this point in several lessons, so hopefully that looks familiar. And it's not wrong to say this is a primary carbon, this is a secondary carbon, and this is a tertiary carbon, just that since the other thing connected to the carbon is a OH, you could also use the term for alcohol as well. Okay, so let's talk a little bit about naming. Now, this is my favorite topic, but the big thing here is that you take the name of the alkane and then you remove the E at the end and you put an OL and you say ol. So ethane becomes ethanol. Methane becomes methanol. So you just change the suffix to an OL. So we'll go ahead and remind ourselves of the different rules of naming and give you some examples. So remember that rule number 1 is that the longest chain needs to include the functional group. So in this case, that longest carbon chain that's going to dictate the parent name must include the OH group, must have in it, in the chain, the carbon that is connected to the OH group. So select the longest carbon chain containing the hydroxyl group and derive the parent name by replacing the E ending with the corresponding alkane with OL. Okay, and then all this should look pretty familiar. So rule number 2, you then number the chain based on the lowest number with respect to the OH group. Okay, so number the chain from the end nearer the hydroxyl group. So, you can see that in the example down here, the numbering goes from left to right because the OH group would be on carbon 2 instead of carbon 1, 2, 3, 4. Okay. And rule number 3, you just, same thing as always, you list the substituents alphabetically with the numbers to indicate their relative positions. Okay, so for example, and before I reveal the answers, I'll just kind of do this. Hopefully I get it right. Part of the reason why I don't like naming, as you've seen before, is I don't always get them correct. So the longest continuous chain here is 5 carbons, 1, 2, 3, 4, 5, right? So it's going to be a pentanol, some version of pentanol, okay? And on carbon 2 is a methyl group. So 2-methyl, 2-methyl, and then 2-pentanol. Okay, so thank you. All right, so over here, we've got the 2 OH group, so it's a diol. That's one, or if it had 3, it would be a triol. So we just incorporate that into the name. It's a cyclohexane ring, okay? And the only things we need to number are the positions of the 2, the alcohol groups, because there's no other substituents. So 1,4, this is a carbon 1 and a carbon 4 dash, and then a cyclohexane diol. Okay, so 2-methyl 2-pentanol. Okay. Oh yeah, the one thing I forgot in this one, this is important, is to indicate the stereochemistry, right? So since they're both on the same face, they're both in the upward face, right? They're both coming out of the screen, then that's why it's called cis. Cis 1,4-hexane diol, cyclohexane diol. Okay, so now let's talk a little bit about naming phenols. Now, my expectations are even lower with phenols because, again, we kind of leave the IUPAC rules behind in many cases. So the word phenol is used as the parent name, not benzene. We're not going to think of the OH as a substituent on benzene. We're going to call it phenol and just name the other substituents accordingly based on their relative positions. So you name the substituents on the aromatic ring by their position from the OH group, from the hydroxyl group. Name substituents on an aromatic ring by their position from OH. Okay, so again, you can see a couple examples here, and many of these have common names. So when you have a methyl group, and it's in the meta position relative to the OH group, the hydroxyl group, so that would be meta-methyl phenol. And over here on the right, you've got 2 nitro groups, and in this case, you can't use the ortho, meta, para designators because you got 3 different substituents. So we go back to the numbering, and if the phenol indicates position number 1, then that means on carbon 2 and carbon 3, 4 are nitro groups, so 2,4-dinitrophenol. Okay, so just an example here. So again, phenol is going to be the basis of the name, so we'll just go ahead and write that down, and we'll just adapt it. Okay, so this is carbon 1, and we want the numbering scheme to be the lowest possible. So that means we're going to go this way towards the methyl group. So this is carbon 2, this is carbon 3, carbon 4. Okay, but we got to put them in alphabetical order. So on carbon 4 is bromo, so 4-bromo. And then on carbon 3 is the methyl, so 3-methyl. Okay. Okay, so what about some properties of alcohols and phenols? Well, first of all, note that they are a hydrogen bond donor and acceptor. A H bond donor and acceptor. Now you see that over here in this diagram, but this diagram just has the interactions between alcohol molecules themselves. So this is specific to methanol, but you could think of these as just R groups. It could be 2 carbons, it could be 17 carbons. Just think of it as the R group. So the other thing that's important to note, though, is these are derivatives of water, so it can interact with water through hydrogen bonding. Let's say that I have H2O just floating around out here, right? There's a hydrogen. The oxygen's got its lone pairs on it, so there's a water molecule. And so that hydrogen can interact with the lone pair on that oxygen to give a hydrogen bond, okay? Or if I've got a, water molecule out here, and it's got its lone pairs on the oxygens, so it can form a hydrogen bond with the hydrogen donated from the alcohol. So it can engage as both an acceptor and a donor in hydrogen bonds with itself or with water or some other potential molecule that can participate in hydrogen bonding. Okay, so that's what drives a lot of its solubility properties and things like that, boiling point, things like that. Okay. All right, now you don't think typically of alcohols as being acids or bases, and you'll see in the table of pKa's there in your handout, that's because the pKa on that hydrogen on the oxygen in alcohol is about the same as what it is for water. These are closely related to water. So that's why when you have a solution of alcohol, it's not going to affect the pH, right? But technically, they can act as a Bronsted acid or base. So we need to remember what those definitions are. A Bronsted base, we'll cover that one first, is when it accepts an H plus. It takes on an H plus. And a Bronsted acid, Bronsted-Lowry acid, is when it would donate its hydrogen in the form of an H plus. So let's talk about, just in theory, how it can behave as a base and as an acid. Either way, it's going to be very, very weakly, about the same extent as water does. So when it behaves as a weak base, what's going on is the oxygen in the OH group is accepting an H plus from strong acids. And probably the terminology is what's most important here. We call that an oxonium ion. So when the alcohol behaves as a base, taking on an H plus from a strong acid, first of all, it can only happen with a really strong acid. Right? It's only going to behave as a base when it's mixed together with a really strong acid. And one of the products we would call an oxonium ion. Kind of like H3O plus, we call that a hydronium ion. Okay. All right, so what does it look like, or what's the theoretical scenario when it's behaving like a weak acid? Well, remember that acid is something that donates H plus. So when an alcohol donates its hydrogen in the form of H plus, first of all, it's only going to be donated to a strong base. It doesn't want to give up that H, but so it's going to require a strong base on the other end to take it. So it's donated to a strong base to produce, again, terminology here is important, something called an alkoxide ion, which is where the oxygen has been stripped of its hydrogen, and so it takes on a formal negative charge. Okay, so a strong base comes along with the curved arrow analysis here, and we'll just finish this up, I guess. So the base grabs that hydrogen because it's got the partial positive charge, and the oxygen has the partial negative charge. And so that bond, it's going to take an H as in the form of an H plus. So this pair of electrons is just going to move onto the oxygen. And that's where you get that third lone pair. We call that an alkoxide. Now, these we deal with more often in organic chemistry. You see these in lots of different organic reactions, these alkoxide ions. Okay, now when the R group is, a benzene ring, we have a special name for the alkoxide. It's called a phenoxide. So it's called phenoxide when R is a benzene ring. And as I said, it takes a strong base. It's not just any old base that's going to do this. So the base must be stronger than the alkoxide. Remember that any acid that it gets stripped of its acidic hydrogen is called a conjugate base. So this RO with a formal negative charge, this alkoxide, behaves as a base itself. And so the base that takes the hydrogen away must be stronger than the alkoxide. And the way you figure that out is you need to compare the pKa's of the two acids, the original acid and the conjugate acid. Okay, compare the pKa's of the conjugate acids. Okay, so we're going to do that in an example. So but before we look at the example, let me show you, what you have there in your handout, this table of pKa's, and it's got some phenols and it's got some alcohols on it. Like this is tertbutyl alcohol, this is ethanol, and relative to water. So as I said, methanol and ethanol are kind of right above and below water on the pKa scale, very close to that of water. So that's why when you have solutions of ethanol, like an alcoholic beverage, its pH is not all that different than what normal water would be. It doesn't affect the pH. Okay, but phenol, as we talked about before, is a weak acid. It's known as a weak acid in aqueous solution because it has a substantially lower pKa than water does. So if you have phenol dissolved in water, it's going to be slightly acidic. And then if you start putting substituents on the phenol, like a chlorine or a nitro group, it becomes even more acidic. Okay, so now let's do this example here. The question is, which direction of the reaction below is favored? So it's a reversible reaction. It's going to establish equilibrium. And when it establishes equilibrium, which is more, which side is favored? Which species are present in higher abundance? Is it going to be this etoxide, this alkoxide, and this CH3SH, or is it going to be ethanol and the CH3S minus? Okay. Well, so what we need to do then is we need to look up the pKa's of the two acids. And so here on the left-hand side, this CH3SH, we can look for that, and that has a pKa of 10.3. Okay. And I look at the table, and ethanol has a pKa of 16. Okay, but now you need to remember, well, what does nature do? Which side does nature favor? And remember, nature favors the side with the weaker acid and base. The weaker acid and base. And the weaker acid is known by a higher pKa, right? If you look at your table again, as you go down, you get stronger acid and you get lower pKa. So the higher pKa is going to be the weaker acid. So this is the weaker acid. And nature favors the side with the weaker acid. And we could also say that this is the weaker base, the CH3S minus. But we don't need to do that. Once you figure out which one is the weaker acid, then you've identified which side is favored. So the right side is favored. Chicken scratch. Okay. And so that means that the reaction is going to proceed more to the right than it does to the left. So if you were to redraw this equilibrium arrow, it would be a bigger arrow pointing right, a smaller arrow pointing left. Okay, because that shows you which side is favored. Okay, so some more properties of alcohols and phenols. We're getting more into the reactions that they undergo. First of all, they will react with a metal, an alkali metal. Remember, those are the metals in the first column of the periodic table: sodium, potassium, lithium. But they also will react with strong bases, as we've already seen, to form those alkoxide ions. So we're going to kind of take this one by one. So first of all, the alcohol reacting with an alkali metal like potassium. So you can see what happens here is actually you form the alkoxide, but with a potassium cation. So each of those potassium atoms, those K atoms, become K plus ions, positive ions, by giving up electron, one each. So it basically gives an electron to a hydrogen, gives an electron to another hydrogen, and you get a hydrogen gas molecule. And in the process, you created 2 potassium ions and 2 moles of the tert butoxide anion. Now, you've seen this molecule before. This is one of those really strong bases that's also really bulky. Okay, we've talked about those with regard to the E2 mechanism and how it's going to, this is, if you use a base like this, you got to take into account the steric hindrance as to which hydrogen is going to get removed in the E2 mechanism. Okay, so you can go back and review that if you want to. But this would be one of those really bulky, strong bases that we talked about. And this would be how you'd make it. So you'd get some, get your bottle of tert butyl alcohol and just throw some potassium in there, and you're going to create that potassium tert butoxide. Okay. All right. So the other part of this, bullet says that it reacts with strong bases. So here's just a couple examples of that. So here's methanol reacting with sodium hydride. Now remember that sodium hydride, that's an ionic compound where the sodium has got the plus charge, positive charge, and the hydride has got the negative charge. Okay. So what's going to happen is, in this alcohol group, that the oxygen is going to have the partial negative charge and the hydrogen is going to have the partial positive charge. So here's your nucleophile, and it's going to attack your electrophile there. And so the product is going to be your H2 gas. And so you create this alkoxide, methoxide is what we would call that. And so since it's got a sodium ion there present as well, we would call that sodium methoxide. Okay, don't worry about this other name. Okay. So the hydride is a stronger base than the methoxide ion. That's why the reaction goes in that direction. Okay, here's another one down below it. So this is, again, it's got a sodium +1 ion, but this is what we call amide, NH2 minus. Okay, so this is like an N with 2 hydrogens, and then it also has 2 lone pairs, and it's got a formal negative charge, right? It also is a really strong base. And so same thing is going to happen. So it's going to act as a nucleophile, and it's going to take on that hydrogen, okay, to create, in this case, an ethoxide, because it's got 2 carbons in it. So methoxide because it has 1 carbon, ethoxide because it has 2 carbons. And then the other product in this case is ammonia, NH3. So you compare the two, the strongest base of the mix is going to be the sodium, the amide here. That's why the reaction goes to the right. Okay, so one more. This is our old friend, the Grignard reagent. Remember that? Grignard is how it's spelled, but you say it Grignard reagent. Okay, it's where you had an alkyl halide and you just mix it together with magnesium metal and it forms this. And so remember that the interesting thing about Grignard reagents is it creates a carbanion-like molecule because this part has got the positive charge on it And so this carbon is going to be negative charge. And so what's going to happen is it's going to act as a nucleophile and take on that hydrogen. Okay, and so you see that it's just going to convert into methane. It's going to take that hydrogen from the alcohol and become CH4, methane. And then you've got the alkoxide, and then the magnesium bromide just forms the counter ion to balance out the charge. Okay, and again, we're going to start seeing these Grignard reagents show up a lot more in the reactions for all these different functional groups that we look at. Okay, so that's just, again, some examples of alcohols reacting with alkali metals, like in the case of potassium, or with various strong bases. Hydride is a strong base, amide is a strong base, and this, the carbon in a Grignard reagent acts as a strong base. Okay. Oh, and again, if you want to write these down, I would encourage you to do so. You could still follow that principle that we talked about before, how nature's going to favor the side that is the weaker acid, which is evident in the size of the pKa. So if you look up the pKa for hydrogen, its pKa is 36. If you look up what it is for methanol, it's 15.5. Okay, the next one down, again, ammonia, if you were to look up its pKa, you'd see that it's got a value around 35. Whereas ethanol has a pKa of around 16. So that's why we know that the reaction goes to the right, it favors the right side. They didn't even bother to write, double direction arrows. They put single direction arrows because it's so dominant in one direction to the right that there's really no point in drawing it as a reversible reaction. Okay. And then if you look up the pKa of cyclohexanol, it's around 16 because it's a secondary alcohol. And then if you look at the pKa of methane, it's around 50. So that we know that it favors the right as well. So there's different techniques you can use to kind of decide what your products are going to be in reactions like this. And pKas, looking up the pKas is one of them. And remember, I don't expect you to memorize any pKas. So if it were necessary to answer the question, I'd give them to you. Okay, so some more reactions that alcohols undergo. So first of all, they undergo substitution, and a lot of this is a review. So I'm going to go through this pretty fast and just remind you where we learned about it in the first time. So substitution reactions, alcohols can undergo to become alkyl halides. All right, and that we learned about that in week 10, lessons 1 and 2. Okay, we learned a lot about addition reactions with alkenes that produce alcohols. Oh, no, I'm sorry. Even the substitution reaction was a preparation of an alcohol. You're producing an alcohol. So you start with an alkyl halide and you react it with like a OH minus, a hydroxide ion, and you create an alcohol. Or you can add something across an alkene we learned about in week 8, lesson 3, that will produce alcohols. And there's two, and there's one actually I want to add to our notes, but let's get through the other two. So first of all, remember one of them was called hydroboration. Okay, and again, I'm not going to go into the details. You can just look it up again from that lesson. But one reminder is that with a hydroboration, you get the non-Markovnikov alcohol, meaning that the alcohol is not on the most substituted carbon. It's on the least substituted carbon. But if you needed it to be on the most substituted carbon, then the reagents you would use are the mercury compound, and you do an oxymercuration procedure. So that yields the Markovnikov alcohol product, which again, remember what that means is the OH is just going to end up on the most substituted one. Okay, so the one that, if you want to just find some space, I think there's a little bit of space in your handout. The other one is, let's say that I have an alkene. So here's an alkene, a very crude drawing of an alkene. And we can just add water to that also to get an alcohol. Okay, so if we add a water molecule to an alcohol, or to an alkene, okay, you get, in this case, it would get through CH3. So I guess I better put H's on here. CH3, and then this would be CH2, and then an OH. Okay, and remember we call that hydration. The hydration of the alkene. Now, the reason why it didn't, originally make the list in this slide is because that kind of reaction just requires some pretty extreme conditions. Okay, so typically you'll use catalysts involved in hydroboration or oxymercuration. We're going to look at how to reduce a carbonyl group to get an alcohol. Now, this hopefully looks familiar because you have done this. We took vanillin in the lab and we used sodium boryl hydride to reduce it down to an alcohol. So the reduction of a carbonyl compound gives an alcohol. And the way you do it is you just add a hydrogen to the C double bond O, right? And the hydrogen comes from a reducing agent. So you start with a carbonyl, you add hydrogen to it, and you can see that kind of adds in two places. But the mechanism, as you'll see, the mechanism, the hydrogen from the reducing agent just goes on the carbon. And then in a second step, you'll actually provide the hydrogen that goes on the oxygen. Okay. And just like, there was the primary, secondary, tertiary alcohols, we get certain types of alcohols based on what we are reducing, what type of carbonyl compound we are reducing. So if we reduce a aldehyde, it gives a primary alcohol. So if we take an aldehyde, and again, that's we recognize that because it's got the carbonyl with the carbon group, an R group on one side and a hydrogen on the other side. The hydrogen just adds to that carbon to give us a primary alcohol. This OH group is on a carbon that's connected to one other carbon. And if we reduce a ketone, then we get a secondary alcohol. So once again, the hydrogen goes on the carbon from the reducing agent, okay? And then later on, we'll throw a hydrogen on that oxygen to give us the alcohol functional group. And in this case, that is on a secondary carbon because this carbon is connected to two other R groups, two other carbons. Okay. So again, the mechanism is that you have the nucleophilic hydride from the reducing agent, like sodium boryl hydride, like we did in the lab. It reacts with the electrophilic carbon, the positively polarized electrophilic carbon of the carbonyl group, just like it shows in the diagram. So this is your nucleophile, and that carbon serves as the electrophile. It attacks this one of the electron pairs in the double bond here, moves on to the oxygen to give you the oxide. So this is the alkoxide. Now, in a second step, and again, I hope you remember this, and when you did the reduction of vanillin, one of the things you had to do to work up the reaction was you had to add an acid, 6 molar hydrochloric acid in your case, in that situation. So one of the things that the addition of the acid was doing, it was doing several things, but one of the things that it was doing was it was throwing a hydrogen, an H plus on that alkoxide to produce the alcohol. Okay, so the alkoxide is protonated to yield the alcohol product. Okay. All right, so something else you can do with a carbonyl to get an alcohol, instead of reducing it, is react it with a Grignard reagent. And this, you can get real creative with this, because that R group can be many things. You can create a lot of different Grignard reagents with a lot of different R groups. Those R groups can be primary, secondary, tertiary carbons. They can be alkyl, they can be aryl, they can be vinyl. And we can do this, with lots of different halogens like the chlorines, bromines, iodines. But the point being is that what you're going to do is it's going to act as the nucleophile. Let me get my pen going here. So again, the carbon is going to act as a carbanion. That's got the partial negative charge on it. And the magnesium part's got the partial positive charge on it. So that's going to act as your nucleophile, and it's going to attack the carbon because it's the electrophilic site on that carbonyl. And then the electrons in the double bond move on to the oxygen. And then in the second step, just like before with the reduction, in a second step, you add acid, and that gives you the hydrogen. It protonates the alkoxide. Okay. But the key here is that what you've done is you've used that carbonyl to introduce another carbon-containing group into the product. So that's why it's used a lot. Okay, so that's what you can do with a Grignard reagent to make an alcohol out of a carbonyl compound. Okay, so this is just the mechanism that I already kind of showed you. So the carbanion that's part of the Grignard reagent acts as the nucleophile. You get the alkoxide, and you treat it with acid, and you get an alcohol. So the Grignard reagents act as nucleophilic carbanions. Nucleophilic carbanions. Okay, so here's just several examples. So alcohols from carbonyl compounds, and this is a form of reduction. Remember that we can define reduction as if we decrease the number of carbon-oxygen bonds. That's a evidence of reduction in organic chemistry. So let me just kind of, how much time we got? We got time. So I'm going to kind of talk through some of these, the mechanisms of some of these. So because this Grignard reagent, this carbon is going to be the partial negative end, the magnesium is going to be the partial positive end. So it's going to act as the nucleophile, and it's going to attack that carbon. Okay. And so effectively what you've done is that you've added this cyclohexane ring to this carbon, and you convert it into an alcohol. All right. Same thing here, where that carbon right there is your nucleophile because it's got the partial negative. So it attacks right there. And you add a phenyl ring to, to some sort of substrate, and you get an alcohol after you treat it with an acid to work it up. So that was with an aldehyde. This is an example with an aldehyde. And you got a secondary alcohol as a product. So if you react it with formaldehyde, you get a primary alcohol. If you react it with an aldehyde, you get a secondary alcohol. If you react it with a ketone, okay, once again, this carbon is going to act as your nucleophile. What you get is now you've got a tertiary alcohol because this carbon is connected to 3 other carbons, that carbon, that carbon, that carbon. So you get a tertiary alcohol if you react the Grignard reagent with a ketone. All right, so you can check your work here. Don't overthink it. I mean, basically, you're producing tertiary alcohols in both situations. You're just adding a methyl group. And then the second step there with the treatment with the acid gives you the hydrogen. It protonates the oxygen, so it gives you the actual alcohol group instead of an alkoxide.